Alright, now that we've covered the material in section 1.1, let's do some exercises. Oh, by the way, if you haven't gone through the material of section 1.1, I want you to please go and view the previous video and then come back and continue with this video. So let's start with question number 1 in the exercises. It says, which of these sentences are propositions? What are the truth values of those that are propositions? So let's start with the A. A says Boston is the capital of Massachusetts. Let me remind you that the definition of a proposition is a sentence that declares a fact. So based on this definition, we can see that the first one is a proposition, so we can say yes, it's a proposition. And the truth value for this case is going to be true because we all know that Boston is the capital of Massachusetts. Go to B. B says Miami is the capital of Florida, and this means that, well, according to the definition, this yields that yes, this is a proposition, and the truth value is also true because we know that Miami is the capital of Florida. Look at C. 2 plus 3 equals 5. This is also a proposition, so we say yes, it is a proposition, and the truth value for this proposition is true. How about 5 plus 7? 5 plus 7 equals 10. Is this a proposition? Yes, it is. So we're going to write yes. And what is the truth value for this proposition? The truth value for this proposition is false. Look at E. X plus 2 equals 211. Now E is not a proposition, so we say no. The reason for that is we're not able to say, or we're not able to assert whether this statement, the outcome of this statement is true or false, and hence this is not a proposition. Mind you that if the value of x is known, then this statement will turn into a proposition, and then based on the value of x we can for sure say whether this proposition is true or false. But because the value of x is not known right now, we cannot, this is not a proposition. Answer this question. Question F, the statement in question F is answer this question, and I'm sure you agree with me that the answer is no, because this is not stating any fact. Now question 2 is similar to question 1. It's giving us a bunch of statements here. We want to see whether these statements are propositions or not. In the same fashion, we can see that 2a, do not pass go, is not a proposition because we don't know we cannot assert the truth value of this statement. The same way, what time is it? This is also not a proposition, so we'll say no. And if you recall, this statement was also part of the examples in the material that we have covered in the beginning of the previous video. So now coming to question 2c, there are no black flies in Maine. Now in this case, this is stating a fact, so we can say for sure that this is a proposition. Now the truth value of the proposition, to be honest with you, I haven't been to Maine, but for any person who has been to Maine, he can make sure whether there are black flies in Maine or not. So if the person did encounter any black flies in Maine, then the truth value can be true. If not, then the truth value is false. So based on our experience or a personal experience, we can still determine the truth value for this statement. So I'm going to just leave it blank over here because I haven't been to main, so I cannot determine the truth value. But keep in mind that if somebody investigates a little bit further, they can determine the truth value, whether it is true or false. Right, let's move on to question number 3. Question number 3 says, what is the negation of each of these propositions? Now, let me remind you that for negation, we have a definition, and the definition says that to negate a proposition P, it is sufficient to just put or affix that proposition with the statement, it is not the case. So let's apply the definition directly. Let's look at 3a. 3a says May has an MP3 player. Let me denote this by the proposition variable P. So in this case, I can for sure say not P can be written as it is not the case that May has an MP3 player. Now, somebody might say that we can rewrite this in a more simpler and more expressive way, and that is true. We can rewrite that as saying May does not have an MP3 player. And basically, whether you write it in the first form or the second form, they're both logically equivalent. And I always advise my students to follow the definition rather than trying to rewrite the expressions in a different way. The reason for that is quite often when you're working with more complex statements or propositions or even compound propositions, writing the negation is not as easy or straightforward as it is in this example. So my advice to everybody is follow the definition as it is, because that is going to through that you're going to avoid any ambiguity or confusion. So let's look at 3b. 3b says there is no pollution in New Jersey. So let me denote this by the proposition variable Q, and then not Q can be written as it is not the case that, and then we put this the proposition there is no pollution in New Jersey. Now we can rewrite this if we want to. So in this way, we can say there is pollution in New Jersey. Okay, now let's go to 3c and see how we can negate that. 3c says 2 plus 1 equals to 3. Let me denote this by the proposition variable R. Then not R can be written as it is not the case that 2 plus 1 equals to 3, and we can also write it as 2 plus 1 does not equal to 3. So whether you write it in this form or whether you write it or whether you apply the definition directly, it's logically equivalent. The last one is 3D, which says the summer in Maine is hot and sunny. If I represent this with the logical variable S, then not S can be written as it is not the case that, and then we write the statement or the proposition, the summer in Maine is hot and sunny. And of course you can re-express this this negation by saying the summer in Maine is not hot and sunny. So we're done with this question. Let's move on to uh, to to the next question. Question 4 is very similar to question 3, and in this case, I'm just going to answer this question in very short sentences. I'll start with question number 4a. 4a says Jennifer and Tia are friends. Let me represent this with the propositional variable p. The not p could be, in this case, let me follow the definition first, and then we'll come and have a discussion on how we can rewrite this, re-express this negation. So using the definition, we can say it is not the case that Jennifer and Tia are friends. Now, we can re-express this in several different ways. We can say that Jennifer and Tia are not friends. We can also say Jennifer and Tia are enemies. So you can see in natural language there are several different ways you can express the same fact, and this most often is the main reason for confusion in ambiguity. That's why I always advise my students, and I always practice it myself, that I apply the definition directly without interfering or without using my language skills to try to be creative to avoid the confusion. Now, the same way over here, if you look at 4b, 4b says there are 13 items in a baker's dozen. So what I can do is I'll denote this by the propositional variable q, and then not q. I can write it just by applying the definition, saying it is not the case that, and then write the statement, the proposition, sorry. Whoops, I've got a rogue screen. Let me just put the screen back as it was. Where is it? Like this and like this, I believe so. So let's continue. So it is not the case that there are 13 items in a baker's dozen. So now I'm sure that after we have covered 6 different examples of negation, I'm sure you'll be able to do 4C and 4D by yourself. The best, as I mentioned, the best way to do that is just to apply the definition directly to avoid any kind of ambiguity or any confusion. Let's continue with question number 8. Question number 8 says, let P and Q be the propositions as follows. P is the proposition, I bought a lottery ticket this week. Q is the proposition, I won the $1 million jackpot. Now, the question is asking us to express each of the propositions, the given propositions, in English sentences. So let's start with A. A is asking me to express negation of P. Oops, the screen jumped out again. Right, so let me negate P. Negation of P can be written as, of course, in negation, as I said earlier, I'm going to apply the definition directly. I'm going to say it is not the case that I bought a lottery ticket this week. Now you can become creative and re-express it in a different way. You can say I did not buy a lottery ticket this week, and in any other way that expresses the same fact using different words. Now let's go to B. B is asking me to write P or Q. Now In the same way, I'm going to use the definition directly. So the definition says that the disjunction between two propositions is the connecting these two propositions using the or operator, and that's what I'm going to do. So I'm going to write the first proposition: I bought a lottery ticket this week, and then I'm going to put the connective or, and then I'm going to write the second proposition: I won the $1 million jackpot. Now, once we know how the proposition can be written in the English language, you can be creative and you may try to re-express it in a different way so that it becomes more expressive in shorter words. Now I'm going to do the same thing with proposition C, but before I do that, let me point out that the compound proposition D, P and Q can also be written similar to what we have done with question B over here. So let me write that these two are quite similar. All the difference is the connective value, the operator over here is going to be and instead of an or. So let's go to C, and C is asking me to express the compound proposition P implies Q. Now, we've seen in the previous lecture or the video that the conditional statements can be expressed in the English language using several different expressions. So here's just a review, just to remind you about the different ways to express the conditional statements. Here we can say P implies Q can be written as if P then Q. P implies Q can also be written as if P, comma Q, or even we can use P only if Q, Q is necessary for P, and so on. So now the choice is ours. In the exercise, the way we answer this question, the choice is ours. We can choose any of those expressions to answer this question. Now, the most straightforward one is the first one, if P then Q. So I'll be using that to express this compound statement. So I'm going to apply it directly. If P in our case is I bought a lottery ticket this week, then Q is the next step. So Q is I won the $1 million jackpot. Now, as you've noticed that the expression that we produced, it might be grammatically that there is some grammatical issue with it, but as far as logic is concerned, we have applied the definition, and this after applying the definition, this expression is logically equivalent to the compound proposition P implies Q. You can now be creative and re-express this in any way you want, but keep in mind that the resultant expression that you'll come up with should be logically equivalent to what we have written over here. So if I was a linguist and working with languages, I might be more concerned with the grammar rather than the logical structure of this statement. But because I'm working in logic, as far as logic is concerned, this expression, in my opinion, is logically correct and is enough for a person who's working in logic to assert that it is logically, or it is expressing P implies Q. And basically The same way you can do question 8E, 8F, 8G. Just apply the definition directly. And of course, let me remind you that for the bidirectional operators, or the bidirectional statements, we also have three different, or we've seen three different ways to express the compound propositions. And when you when you are trying to answer question 8E, just apply one of those expressions, and that would be enough. And logically, the result that you'll have will be logically equivalent to the compound expression that you're trying to translate in or express in the English language. Right. Let me continue with question 11. Question 11 says, let P and Q be the propositions. P is, it is below freezing. Q, it is snowing. Now the question is asking us to write these propositions using P and Q and logic connectives, including the negations. So now what we are asked to do is the opposite of question 8. Let me scroll back to question 8. Question 8 gave us the propositions in plain English, and then the question asked us to convert mathematical notation into English sentences. Question 11 is asking us the opposite. Question 11 is giving us the statements, the compounds propositions in the English language, and asking us to convert it into mathematical notations. So let's do that. Starting with 11a. 11a says it is below freezing and snowing. So let's identify the propositions first. I can see that this is the first part of the statement, and this is according to the what is given is proposition P, and it is snowing is proposition Q, and the connective over here is the AND operator. So I can safely say that this can be represented mathematically as P and Q. Let's look at 11b. 11b says it is below freezing but not snowing. There you go. Let me first go identify the propositions. This is the first proposition, this is the second proposition, and then we have what? Not over here, so there's a negation. And but over here, if you recall from the previous lecture video, we had mentioned that in natural language and but are extensively used interchangeably in expressing the AND operator. So in this case, what I see is we've got the P proposition here, the Q proposition here, and we have a negation, so I can safely say that this statement can be written in mathematical terms as P and not Q. Continuing with this question, let's look at 11c. 11c says it is not below freezing. There you go. I have now identified that this is the proposition P, and it is not snowing, so this is proposition Q. And we have negation over here, and the connective operator here, so I can safely say that this can be represented as not P and not Q. Let's go for the next one. 11d. 11d says it is either snowing or below freezing or both. If you recall, when we were covering the conjunction and the disjunction, we said that the OR operator that we use in logic is the inclusive OR, and this statement is basically giving us a hint with this or both part that this is the inclusive OR, not the exclusive OR. So I know that the connective is now inclusive OR, so let me write the connective inclusive OR, or in short. And basically, the first part here is snowing. Snowing is Q according to the question, and below freezing is P. So let me put this into perspective. There you go. Below freezing is P, snowing is Q, and we know the operator is OR, so this can be written as P or Q. We can also, if you want to observe the order of the statements, you can also write it as Q or P, and we know that the truth value of Q, P, or Q, or Q, or P is the same thing. Now, let's look at 11E. 11E says, if it is below freezing, it is also snowing. Now, I'm sure you must have noticed that this expression is very similar to the conditional expression, the second conditional expression over here, if P comma Q. So for sure we can say that we have the implication or a conditional statement over here. Just to identify the propositions, below freezing is proposition P, snowing is proposition Q, so I can for sure or safely say that this can be written as P implies Q. Now let's go to 11F. 11F is a more complex example. Let me read it out first. Either it is below freezing or it is snowing, but it is not snowing if it is below freezing. So let me identify the connective first. So here's one connective, or, but is another connective, which is the AND connective. And here, well, the if statement is giving me the hint that there is an implication or a conditional statement. Let me just first of all write down the connectives. So we got an OR, and we got an and we got an implication. Now all we need to do is identify the propositions and put the propositions in their proper place. So either it is below freezing or not snowing. Below freezing is the proposition P, as we know. Is snowing is the proposition Q, so you got P, Q, and this is 1, a compound statement. But it is not snowing if it is below freezing. Now let me go back to the different expressions that can be used to express the conditional statement, and you'll notice that Q if P, it matches the example that we have over here. So this means whatever the first one is going to be whatever coming before if is going to be on the right side of the conditional operator, or the implies operator. So snowing is Q and freezing is P, so I can safely say this is P implies Q. But wait a minute, I've got the not operator here, so there should be a not sign over here, and this goes in parentheses, and for sure I can now I know that 11F can be rewritten in mathematical notation using this complex expression. Right, let's look at 11G. 11G says that it is below freezing is necessary and sufficient for it to be snowing. Now look at necessary and sufficient. This gives us a hint that this is a bidirectional statement. The reason for that is, if you recall, let me take you to this part of the lecture. As you can see, P is necessary and sufficient for Q is one of the expressions that can be used to express a bidirectional statement. And this is exactly, or it fits exactly with 11G, because of the necessary and sufficient that appears in the middle of the statement. So for safely, I can say that whatever this statement is Q, and this statement is sorry, below freezing. Below freezing is P. So remove that. Put P over here, Q over here, and I can safely say that this can be rewritten as P if and only if Q, and that solves all the questions or in question 11. Right. As you've seen, we're just doing exercises concerning the concepts and the ideas that was covered in session 1.1. Let's continue with this. Going to question number 17. Question number 17 says, determine whether each of the conditional statement is true or false. So we have 4 conditional statements, and we want to know whether the whole conditional statement is true or false. Now, if in order to determine, let me remind you, or let me just write the truth table for the conditional statement here, so that we can use it to determine the truth value of these of the given examples. So we'll start with true, true, false, false for the column of P, and true, false, false for the column of Q. And we know that the conditional statement truth table is true, false, true, true. And a good way to memorize this is that if the second statement, if the second part of the conditional statement is false, then the whole conditional statement has a false truth value. So now let's look at question 17a. Question 17a says, if 1 plus 1 equals 2, then 2 plus 2 is equal to 5. Let's identify the propositions. Let me denote this by P, and let me denote this by Q. So this can be rewritten as P implies Q. Now, what is the value of P in this case? 1 plus 1 equals to 2, so the value of P is true. So this is equivalent to true, implies the value of Q is 2 plus 2 is 5, false. So true implies false, or true and false according to this truth table is false, and hence I can safely say that the whole statement is false. Now we can apply the same thing to 17b and all the others. Let me do 17b now. I will identify this statement as P. We'll identify this statement or proposition as Q. So we've got P implies Q, and in this case 1 plus 1 equals to 3 is false, implies 2 plus 2 is 4 is true, false implies true. In this, and according to this truth table, is equal to true, so I can say that 17b is true, or the truth value for 17b is true. Now the same way, 1 plus 3, if 1 plus 3 equals to, if 1 plus 1 equals to 3, then 2 plus 2 equals 5. This can be written as P implies Q. In this case, 1 plus 1 equals to 3 is false, and 2 plus 2 is equal to 5 is also false. False implies false according to the truth table is true, so I can safely say that 17c is also true. Let's look at 17d. 17d says, if monkeys can fly, then 1 plus 1 equals to 3. Let's look at the first proposition. Monkeys can fly, let's denote it by P. Then 1 plus 1 equals to 3, let's denote it by Q. And here we have P implies Q. And let's look at the truth table, the truth value of this statement using the truth table. So monkeys can fly we know that that is false. And 1 plus 1 equals 3, that is also false. False implies false, gives us the whole value to be true. So we can safely say that 17D is also true. Now, keep in mind that 17D is a very good example where they don't have to be any relationship between the first proposition and the second proposition in the conditional statement, because all we are concerned with in so far is just to apply the definition, regardless of the actual meaning of that, because only the context of the conditional statement can express the meaning of what the conditional statement is talking about. But for exercise purposes, all we are concerned with is just the definition and nothing more so far. So let me cover question number 27. Question 27 says, state the converse, the contrapositive, and the inverse of each of these conditional statements. If you recall, we've seen that converse, contrapositive, and inverse are related to the conditional statement. So if we have a conditional statement, P implies Q, then the converse is written as Q implies P. The contrapositive is expressed as not Q implies not P, and the inverse is expressed as, whoops, rogue screen, okay, here we go. The inverse is expressed as not P implies not Q. And to refresh your memory, let me take you back to that part of the lecture, and here is the definition of the converse, contrapositive, and the inverse, and we summarized it earlier like this, and I've just rewritten it over here again so that it's going to be a reference for us while we answer this question. So question 27a says, if it snows today, I will ski tomorrow. So the first thing we need to do is identify the two propositions P and Q. So from A, we can see that P is the proposition if it snows today. The proposition without the if, of course. And Q is the proposition I will ski tomorrow. I will ski tomorrow. Right, now let's look at the converse. So the converse is expressed as Q implies P, and of course we can say, we can write it in the English language by saying if, and I will ski tomorrow, then, and P, it snows today. Now, if you look at this expression, although we have applied the definition directly, the sentence does not make a lot of sense. It seems more like Yoda talking than normal people talking. So what we can do is we can go back to the conditional statements, the different expressions that can be used to express the conditional statements, and just try to find out which one fits our situation best. I believe that P only if Q is more suitable over here. So I can safely say that this can be rewritten as I will ski tomorrow only if it snows today. There you go. This is logically equivalent to the previous one and logically equivalent to the converse, and it sounds good as well when when somebody says it, when you hear it. And if somebody says it, oops, I've got rogue screen again. I need some more space, so I'm just going to move this a little bit to the bottom. Okay. So we're done with the converse. Let's go with the contrapositive. The contrapositive, according to the definition, is not Q implies not P. Now, first what I'm going to do is I'm going to apply the definition as is. Now, negation of Q, I can say it is not the case that Q, and Q we define it as I will ski tomorrow. I will ski tomorrow. Okay, so this is the not Q. And for the conditional statement, I can put an if over here. So the statement is, if it is not the case that I will ski tomorrow, then, and I don't want to put the negation of P, so negation, I'll follow the definition. It is not the case that it snows today. It snows today. Now, there you go. Yoda talk again. So, to make it sound more reasonable and make more sense, we can rewrite this as follows. If I do not ski tomorrow, then it will not have snowed today. And this sounds a little bit better and logically equivalent to the previous one. And let me repeat that again. For me personally, as far as logic is concerned, if some student comes up with this expression, then I would consider this expression to be enough to express, because I'm not Shakespeare, and this is not English literature class anyway. This is just logic class. But of course, if you want to be more creative, that's upon you. And keep in mind that whatever expression you end up with should be logically equivalent to the previous one. So the next one is the inverse. The inverse, as you've seen, is not P implies not Q. So let me write over here. Inverse is not P implies not Q. Now I'm going to skip the definition, the direct application of definition, and I'm going to write the short expression, or the expression that makes more sense instead of sounding like Yoda. So the inverse, let me just put that into perspective. So the inverse is not P, so it's not the case that it snows today, and implies not Q. It's not the case that I will ski tomorrow. So not P, not Q can be written as if it does not snow today. This is the negation of P. Then I will not ski tomorrow. And there you go. This is the inverse of the conditional statement that is given in 27A. Now I'm going to leave 27B and 27C for you to do it yourself, but I'm sure that if you have followed what I have done carefully over here, you'll be able to um, do 27B and 27C with no issues at all. Right. The last question I'm going to cover in this video is question number 35. Well, I'm not going to cover the whole question. I'm going to cover a portion of it. I'll leave the rest for you. I mean, what's the use of me doing all the exercises? Because you are the one who needs to learn it, so you have to do the exercises. I'm just going to give you just pointers through these videos. So, um, question 35 says, construct a truth table for each of these compound propositions. So let's start with A. We've got P implies not Q. So I'm going to start building the truth table. We have P and Q, two propositional variables, and for P I'm going to populate the column with true, true, false, false. Let me just separate this two rows in one section, and I'm going to populate the column for Q with true, false, true, false. Just a reminder, I'm doing this in such a pattern because I want all the different combinations of true and false to exist in this table. And hence we got two trues and two false, and then true, false, or one alternate between the true and false for the second column, and you get that combination, all the combinations. Now, for P implies not Q, we need the truth value for the negation of Q. So I'm going to dedicate another column for the negation of Q. Negation of Q is just the opposite truth value for whatever we have for true. So if Q is true, the negation of true is false. If Q is false, the negation of Q is true. So here we'll have false, and here we will have true. Now that all my columns are ready for so all the truth values for all the different components are ready, I can calculate P implies not Q. And if you recall, let me just scroll back to the top over here. The truth table for the conditional statement is given over here. So you got true. It's only false when the second component is false. So let's apply the same thing over here. We got P, so we are basically going to take this column, and we're going to use them to create the truth values for P implies not Q. So true implies false is false. This is the only case where it's going to be false. True implies true is true according to the truth table of the conditional statement, sorry. And false implies false is true, and false implies true is also true. And there you go. This is the truth value for this statement, or the truth table for statement A, or question A. Now let me do the other one, another one. Instead of doing B, let me do C. And C, in C we need, as you can see, we still need two. Let me rewrite C again over here, so we got P implies Q, or not P implies Q. So let me just build the truth table for that. So I'm going to start with a column for P with true, true, false, false, and Q, true, false, true, false. Now let's see what other components I need. You'll notice that we need not P, negation of P. So let me put negation of P here and dedicate this. Negation of P, as you can see, is going to be false, false, true, true. What else do I need? I need P implies Q. So P implies Q over here. What else? I need not P implies Q. And then the last one that I need is the whole statement. P implies Q, or not P implies Q. So P implies Q. This is Just going back to the truth table of the conditional statement, we can say that P implies Q will give us true, false, true, true. Was that too fast? I'm sure not. Okay. Now, not P implies Q. We got not P implies Q. So we got false implies true is true. False implies false is true. True implies true is true. True implies false is false. See, it's only false when the second part is false. Now we need to calculate the truth value for the whole statement, and we need to apply the disjunction function. So we need to use the truth value for the or truth table. Let me just remind you that the truth table for the disjunction, not conjunction, disjunction. The truth table for the disjunction is in front of you here, and we only have false when both of them are false. Otherwise, we have the value of true. So let's do that over here. So we'll take the left part and which is depicted here, and the right part which is depicted here, and we're going to use these two columns to calculate the truth value for the original statement. So true or true is true, false or true is true, true or true is true, and true or false is true. So the truth value for this statement is, or the truth table for this whole compound statement is given over here. Right, so through these exercises I have basically covered all the concepts that were explained in the previous lecture or the previous tutorial and video. I do advise you to please go to the textbook and do the exercises that are after section 1.1. The more exercise you'll do, the better you'll have, the better command you'll have on propositional logic. I wish you all the best and see you in the next video.